Fortunately, nowadays, many systems provide hardware supported to implement a critical section. So all solutions are based on idea of locking. So which means that when you want to access the critical section, you have to access the lock. So as long as you get the lock, you can access the critical section. Otherwise, you have to wait until you get the lock. On the other hand, for the hardware supports uniprocessor, so only one processor in the system and only one core in the processor. Another solution can be used to address the critical section problem and simply disable the interrupt. So since the interruption has been disabled, the current process can execute in the CPU without any preemption. So as long as the process wants to execute in the CPU, no one can kick it off from the CPU. So even the operating system. Since there's no preemption, so we can guarantee there's no critical section issues there. Because while this process accesses the shared data, so no one else can access the shared data because no one else can access the CPU as long as this process still wants to stay in the CPU. However, although it can address critical section problem, so generally in nowadays computer system with multiple processors and multiple cores in each processor, so simply disable the interrupts can make the computer system much more inefficient. So even though it can guarantee the correctness, as we already mentioned in the previous chapter, so when we design the operating system, only guarantee the correctness may not be enough. So we also need to consider the performance and the efficiency. So in order to address the critical section problem more efficiently on multiple core systems, so we need to figure out other ways. In modern machine, so we usually define special atomic hardware instructions. The atomic hardware instructions means that so we want to execute instruction as a single uninterruptible unit. The atomic instruction may take several steps to execute the instructions as a single, means those steps have to be run in whole or not be run. So you cannot run part of those steps, then run other instructions. That is not allowed. So either all or none. It can never be stopped at the middle of the execution. That is why we call it uninterruptible unit. So one example is a text and a set. So we will go through this example in the next few slides. The definition of a text and a set instruction is that so we define a function called text and set, which will return a Boolean variable. And this function will accept a Boolean pointer as a parameter. Inside the function, so there are three steps. The first step will store the original value inside the Boolean pointer type parameter into a Boolean variable RV. Then assign a new value true into the parameter. The last step will return the Boolean variable stored in RV, which is the original value of the parameter, back to the user. So for these three steps must be executed atomically, which means it cannot be interrupted in the middle of the execution. Then returns original value of the passed in parameter to the user, and also set a new value of the passed in parameter to true. Then let's look at a real example to see how the test and the set function works to address the critical section problem. At the very beginning, the shared Boolean variable lock will be initialized as false. So in the solution, we can use the test and the set for different processes to access the critical section without any risk condition. So here, we just assume all the processes have the same code shown on the slide. For illustration purpose, so let's look at the two processes, P1 and P2. Then let's assume P1 is on the CPU first. So when P1 execute the while loop instruction, as we have mentioned in the previous slide, the test and the set function will return the old value of lock, which is false, then set the lock to true. Then process P1 will be out of the while loop and run in the critical section. However, at this moment, the interruption is triggered. Then P2 has been put onto the CPU. The while loop of P2 is executed. So since now the value of lock is true, so P2 will be stuck at the while loop and still set the value of lock as true. Then the interruption is happened, so P1 is put back. Then the value of lock is changed to false. Then run the remainder section. Then interrupted by P2 again. So since currently the lock has been changed to false, so P2 will be out of the while loop and access the critical section. Then P2 is interrupted by P1. Then P1 is blocked by the while loop due to the value of lock is true now. So from this example, you can see that both P1 and P2 can access the critical section without any race condition issue there. And also, both P1 and P2 can make progress concurrently. As we have mentioned in the previous slide, to address the critical section problem, the solution should satisfy three requirements, which are mutual exclusion, progress, and bounded waiting. So seems like the current solution can satisfy both mutual exclusion and progress without any problem. And then let's see if it can satisfy the third requirement or not. So let's assume another situation between P1 and P2. So still P1 is in the CPU first. P1 execute the while loop, then set the lock to true and out of the while loop, then get into critical section. After that, the interruption is triggered. Then P2 is loaded into the CPU. Then P2 is stuck at the while loop due to the value of lock currently is true now. Then P2 is interrupted by P1. Then P1 changes the lock to false and run the remainder section and then do another loop. Then P1 executes the while loop again. Since the value of loop is false, so P1 is out of the while loop, then access the critical section. And then being interrupted by P2, and the process P2 is still stuck at the while loop until it is interrupted by P1. Then P1 continue the progress. So from this scenario, you may already see the problem. Process P2 is stuck there forever without making any progress. So which means that even the previous two requirements can be fulfilled, the bounded waiting requirement cannot be satisfied in this situation. So later, let's see how we can change this solution to make it can fulfill the third requirement.